All right, so okay, so here we have three functions, um, f of x, h of x, and g of x, and I have the with the point C on the x-axis, and that point C marks the inflection point where the graph switches its uh, concavity. But take the graph f of x here, left of C, the derivative of x is greater than zero, meaning that over this stretch right here, when x is less than c, um, the graph is increasing, and that's the inverse for when for x is greater than c, less than zero. That means that the function is decreasing. So because of that, we can mark c is a critical point. The graph is increasing, and on this side, the graph is decreasing, meaning that up here we have a local maximum, or because there's the switch from increasing to decreasing, that means that there's a critical point. Critical point, and I'll write plus local max. So that's just for f of x. Now take h of x. When x is less than c, the graph is going down. It's decreasing, and that's once again the opposite of after the point c on the x-axis. Here, take a point here, took a point here, draw a secant line through there. Your graph is increasing. The slope of that line is positive. The graph is increasing, and that's given to us using calculus through the derivative at over this interval being greater than zero. So because we have negative here and positive here, that's another critical point. There's also a local minimum here. F of x, we have a local max because there's a switch from negative rate of change to positive rate of change. So we're going to do negative, positive, and that's given to us by the derivative being greater than zero. Or sorry, wait, my mistake. So here, um, it's increasing, and then at the point C, it starts decreasing again, and that means that there's a critical point and a local max. Because if you're reading the graph from left to right, it goes positive and then negative, and then right at the very top, the local max. Now, for the opposite of that, for a local minimum, the derivative would be less than zero before, so the graph is decreasing, so negative here. And then once it crosses that inflection point, the point C, then it starts increasing again, positive, the derivative is positive, negative to positive, you're reading the graph left to right, critical point plus local min, reading the graph left to right, that means that it's a minimum. Now here, g of x, this is a bit different. So point here, secant line through the 2 points, and our derivative is positive, meaning the function is increasing. Now let's take let's look at when x is greater than c. I have f of x here, my mistake. It should be g of x. Um, when the derivative of g of x is when g prime of x is greater than c, it is also increasing. So we have positive here and positive there. Now, what does that mean? That means that this is a still critical point because at this point, um, uh, g prime of x is zero. So we write that as g prime of c equals zero, which means that there is a critical point at c, um, but it's not a local max or min because you have a positive, the derivative of the function is positive when x is less than c, and positive when x is greater than c. So because there's no change from either negative to positive or positive to negative, that means that there's not a local max or a local min. All right, so um, how do we apply this? We're given a function f of x equals x cubed minus 6x squared plus 9x plus 1. And we are asked to find and classify all the extrema. As a reminder, I just have over here, when the derivative is greater than zero, the function is increasing. when the derivative is less than 0, the function is decreasing. So that's going to be important later. But in order to apply that, we need to start by taking the derivative. So pretty easy function, take the derivative of. We're just going to use just like the exponent rules. I don't know, I was called chain rule or whatever. But we're going to write this as f prime of x equals 3x squared minus 12x plus 9. And then I'll write out plus 0. So x to the 3, bring down the 3, bring the 3 out front, and then minus 1. So it's 3x squared. And we do that for each term. So for 6x squared, bring the 2 out front. 2 times 6 is 12. And then minus 1. So this is to the power of 1 here, but we don't write that. And then here, this is 1 up here. So we're multiplying 9 times 1 and x minus 1. Or x to the 1 minus 1 is x to the 0, and x to the 0 is just 1. So this is 9 times 1 times 1, which is just 9. And then here, because it's just a constant, the derivative of a constant is just 0. And so I'm just going to erase that. So we have a derivative f prime of x equals 3x squared minus 12x plus 9. And I'll make a note here. Critical points are when f prime of x equals 0. So some of you might already see what we need to do. We're just going to set f prime of x, this function here, our derivative, equal to 0, and then solve for x. And then those x values are our critical points. And our critical points are the points where the derivative equals 0. In order to factor this, we can do 0 equals 3x squared minus 12x plus 9. And then we can actually, looking at this, we can actually make this easier on ourselves to just factor on our own. We can make it easier. All these terms are divisible by 3. That means that we can pull out a 3. So we have 3 times x squared minus 4x because 3 or 12 divided by 3 is 4 plus 3 because 9 divided by 3 is 9 or is sorry 9 divided by 3 is 3. So now we have 0 equals 3 times x squared minus 4x plus 3. Now that's a lot easier to factor than this top equation. So it's just both work. It's just a way of simplifying it. We're looking for two numbers that multiply to 3, multiply to positive 3, add to minus 4. So our factors 3 are 3 is a prime number, so it's just 1 and 3. 1 times 3, and we need negative 4. So negative 1 plus negative 3 equals negative 4. So we're going to write x minus 1 times x minus 3 because negative 1 times negative 3 is positive 3, and negative 1 plus negative 3 is negative 4. And then we still have the 3 up front. Now we're just going to solve for our x's. We don't really need to worry about the 3 because we already have that factored out. So we're just going to set x, we're just going to set both these components to 0. So we're going to have x minus 1 equals 0 and x minus 3 equals 0, meaning our x values are 1 and 3. Because you add the 3, add the 1 both sides, x equals 1 and x equals 3. So those are our critical points. Those are the points where the graph, where the derivative of the function equals 0. And as we looked at earlier, that means that there might be a local max or min. Now, in order to check that, we're going to use nice old number line. So this is going to be a number line of our function f of x, or sorry, f prime of x, or our derivative. And we're going to mark down these 2 points because these are really the only points that we care about. So we're going to have 1 right here and then 3. What we're checking for here is we're checking for the sign of the sign of the function, the sign of the derivative of the function before 1, in between 1 and 3, and after 3. And then that will give us a good idea of if there's a local max or min. We have 3 intervals that we're working with here. We have negative infinity to 1. Actually, I'll write out infinity over here. Infinity over there. There's 3 intervals that we're working with here. We have negative infinity to 1, 1 to 3, and 3 to infinity. So when we look at what the sign of the derivative within these intervals, we have to look at a point in between these. We can't just do like 1 or 3. So we're just gonna pick a number between all of them, one number for each of them. And I think we're gonna start with -infinity to 1. Um, and we're just gonna take that number and then we're gonna plug it in to this to see what the sign of the function is. Because remember, if the derivative of the function is greater than 0, if the derivative function is positive, then that means that the graph is increasing. If the derivative is negative, that means that the function is decreasing. And we need that information to know if it's a local max or min. So I'm just gonna pick a point. We're gonna start with 0. So forgive my bad handwriting. F prime is 0. That means that we're gonna be plugging in over here. We're gonna be plugging in 0 for our x values here. So we're gonna do 3 x. Sorry. 0 minus 1 times 0 minus 3. So we could solve that numerically. It's pretty easy to, but I'm lazy and we don't need the actual y value as a result of f prime 0. We just need to know the sign of it. So I'm gonna do this the lazy way and say that 0 minus 3, that's negative. 0 minus 1, that's also negative. 3, that's positive. All those are multiplied together. Negative times a negative is a positive, and positive times a positive is a positive. So that means that between the interval of -infinity to 1, we chose 0. And it's like that for the whole interval. We could have chosen any point between -infinity and 1. Over that whole interval, the derivative of f of x is positive. Now let's pick another one. All right, so for our next interval, it's 1 to 3. So we're just going to pick any point between 1 and 3. I'm going to choose 2 because I just don't feel like dealing with decimals. So 2 minus 1, 3 times 2 minus 1 times 2 minus 3. We don't need to know the actual magnitude of f prime of 2. We just need to know the sign of it. So once again, doing the same thing. You don't multiply together. So 2 minus 3, that's a negative. 2 minus 1, that's a positive. 3, once again, positive. Multiply all this together. Positive times a positive is a positive. Positive times a negative is a negative. And then negative times positive is negative. So that means that between the interval 1 and 3, our our derivative is negative. All right, we got one more, and that is the interval 3, uh, 3 to positive infinity. Let's try doing 10. F prime of 10 comes out to 3 times 10 minus 1 times 10 minus 3. Once again, I don't care about the magnitude of the output of this function. I just want to know the sign of it so I can plug that into my number chart and then figure out if it's a local max or a local min. So 3, that's a positive. 10 minus 1, that comes out to 9, which is positive. And then 10 minus 3, that's also positive. You multiply those together because they're multiplied in the function here. Positive times a positive is big old positive. So that means that between 3 and infinity, all the points between 3 and infinity, the graph is positive. So what does that mean? If you recall from earlier, let's say we have a graph. So we have a graph here. If the slope of that graph goes positive, crosses the point, and then goes to negative, that's a local max. Inversely, if you have a graph that goes negative, across the point, and then goes positive, that's a local minimum. And remember here, we're talking about the slope of the graph. So let's apply that to this function here. So we have a positive going to a negative. So what does that look like? That is a local max. So that means that we have a, let's write max. We have a max at x equals 1 because the slope of the graph goes positive to negative. Going up, reaches the point 1. This is 1 right here. And then starts going negative again And because it goes negative again, it goes positive and negative, that results in a local max. Now, for this interval, 1 to 3, the graph is going, or the slope of the graph is going negative to positive. So that means that the graph is decreasing and then increasing. Once again, take a second, figure this out, but I think you probably got this. I'll still draw out what it looks like. So function is decreasing, coming down from the top here, crosses the point, and then starts increasing again. It's going from negative to positive. And in this point, in this case, is 3. So negative to positive, negative to positive. What does that result in? Local minimum. That means that at x equals 3, we have a minimum. All right, so we're pretty much done at this point. Um, I'm just going to put into a nice little answer. So for f of x equals our original function, I almost just fell over. Our original function is x cubed minus 6x squared uh, plus 9x plus 1. Um, we have a local maximum. We have a local max at x equals 1, and we have a local minimum at x equals 3. And that's our final answer right there. Oh, also, I should have noted, hmm, yeah, I should have had this as step 2. So we're just going to overview this again. We have our original function, f of x equals x cubed minus 6x squared plus 9x plus 1. Actually, do I have water? So, remember to take your water break, guys. Drink up. Um, yeah, so we have our original function, f of x equals x cubed minus 6x squared plus 9x plus 1. And then we start out by taking the derivative of that function. Or, sorry, our original function, and the question wants us to find and classify all extrema. So that means all the local max and mins. Just gotta find the x value for those local max and mins, and then find out if they're local max or mins. So, starting out, we're going to take the derivative of this because in order to find the x value of the local max or mins, we need to take the derivative and then set that to 0. So taking the derivative, we use, I think it's just called exponent rules. I really don't know the name of it for derivatives. The basic way that we were all taught the first time you took a derivative. Um, bring 3 down out front, 3x squared minus 2 times 6, 12, 12x to the 1 plus 9. And then 1, the derivative of 1 is just 0. So I don't bother writing that. Um, then, in order to find our critical points are defined as points where the derivative of a function is equal to 0. So we have the derivative of a function. We know we have to set it to 0. So we set it to 0. And then we solve for x. We can do this by factoring. And so we start out by pulling out the 3 just to make it easier for ourselves. You don't have to if you don't want to, but in this case, it just makes it easier and it still works out. Um, so we have 0 um, equals 3 times x squared minus 4x plus 3. And then we factored out the x's and sides to get x minus 1, x minus 3, because remember, we need two numbers that multiply to positive 3 and add to negative 4. So negative 3 or negative 1 times negative 3 comes out to positive 3, and negative 1 plus negative 3 comes out to negative 4. So that's how we know those numbers are right. And then we set each of these equal to 0 right here, and then solve for x. So we have x equals 1 and x equals 3. That's our first step. These are our critical points because these are the points where the derivative of the function equals 0. Then, I didn't write this before, but I should have written this as our next step. Next up, we made a number line, and then we marked on the number line our critical points and then our infinities. And then from there, our next step is to find if the derivative of the function is increasing or decreasing within the intervals set up on our number line. So over here, remember, if the derivative of the function is greater than zero, that means that the function is increasing. And if the derivative of the function is less than zero, then that means that the function is decreasing. So positive, increasing, sorry, positive, increasing, negative, decreasing. Um, and so I just plugged in numbers at each point. Here, I plugged in for the interval negative infinity to one, I plugged in zero. That came out to positive. I just plugged into to this right here just because it's the easier form, and I just looked at the sign of the function. So I plugged in zero, realized oh negative, negative, positive. Three is positive. Zero minus one is negative. Zero minus three is negative. So positive times a negative times a negative. Negative times a negative is a positive. Positive times a positive is a positive. So that means that the interval negative infinity to one is positive. And then I did the same thing for all the other intervals. I did the same thing for one to three, and I did the same thing for three to infinity. For one to three, I just chose the point two because I didn't want to have to deal with decimals. And then for the interval three to infinity, I chose yeah 10. Then and same thing here. Three is positive, 10 minus one is positive, 10 minus three is positive. All these are multiplied together to get a positive value, meaning that in this interval, the derivative of the function is positive. Now, and then went through the examples where, let's draw them out here. Whoops. If you recall from earlier, when we were looking at the graphs, um, going from a positive rate of change to negative rate of change, and it flips at this line right here down the middle. Going from a positive rate of change to a negative point rate of change looks like this on the graph, and this is a maximum right here. So that means that because uh, when the function was left of one, it was positive, and when it was right of one, it was negative. That means that we have a local max at one. And then for three, if you recall, um, when the left of a point is negative and the and to the right, it's the function is or the derivative is positive. That means that there's a minimum because it's minimum. It's going down and then it's going right back up. It's a minimum, and then so it means that we have a minimum at three, at x equals three, and I just put down all nice answer. For our function f of x, we have a local maximum at x equals one because it went from positive. The derivative went from positive to negative, and we have a local minimum at x equals three. Sorry about that. Um, because the derivative of the function goes from negative to positive. And yeah, that's pretty much it. Yeah.